Mechanical properties of fluid. In this chapter, we shall study some common physical properties of liquids and gases. Liquids and gases can flow and therefore are called fluids. It is the property that distinguishes liquids and gases from solids in a basic way. Fluids are everywhere around us. Earth has an envelope of air and 2/3 of its surface is covered with water. Water is not only necessary for our existence, every mammalian body constitutes mostly of water. All the processes occurring in living beings, including plants, are mediated by fluids. Thus, understanding the behavior and properties of fluids is important. How are fluids different from solids? What is common in liquids and gases? Unlike a solid, a fluid has no definite shape of its own. Solids and liquids have a fixed volume, whereas a gas fills the entire volume of the container. We have learned in the previous chapter that the volume of a solid can be changed by stress. I repeat, volume of a solid can be changed by stress. The volume of a solid, liquid, or gas depends on the stress or pressure acting on it. When we talk about fixed volume of a solid or liquid, we mean its volume is under atmospheric pressure. The difference between gas and solid or liquids is that for solids or liquids, the change in volume is due to change of external pressure rather small. So the difference between gases and solids or liquids is that for solids or liquids, the change in volume due to external pressure is rather small. In other words, solids and liquids have much lower compressibility as compared to gases. Shear stress can change the shape of a solid, keeping its volume fixed. If the volume is to be kept fixed and the shape of the solid has to be changed, we apply a shear stress. The key property of fluids is that they offer very little resistance to shear stress. So their shape changes by application of very small shear stress. थोड़े से stress में shape change होने लगता है. The shearing stress of fluid is about million times smaller than that of solids. So solids can, resist compression. They can resist compression very well, much more than that of fluids, liquids and gases. Liquids also can resist compression till a certain extent, but gases do not have the ability to resist compression. Pressure. A sharp needle, when pressed against our skin, pierces it. Our skin, however, remains intact when a blunt object with a wider contact area, say the back of a spoon, is pressed against it with the same force. If an elephant were to step on a man's chest, his ribs would crack. A circus performer across whose chest is large, light but strong wooden plank is placed first is safe from the accident. Why? Such everyday experiences convince us that both the force and its coverage area are important. How much force is acting is also important, and what is the area on which is it acting? Is the area small comparatively? Is the area very large? Is the area large, or is the area very small? So it also depends on the magnitude of force as well as the area. Smaller the area on which the force acts, greater is the impact. जितना कम एरिया पे फोर्स एक्ट करेगा, जितना कम एरिया और जितना ज़्यादा फोर्स, उतना ज़्यादा प्रेशर. एंड दिस इम्पैक्ट, द इम्पैक्ट विच इज गिव इज कॉल्ड प्रेशर. जितना ज़्यादा फोर्स से हम नीडल को प्रेस करेंगे, उतनी जल्दी वो स्किन को पियर्स करेगी, उतनी ज़्यादा पियर्स करेगी. और स्किन का एरिया अगर बड़ा हो, देन द pressure will be small. If the area is small and the force is large, the pressure has to be large. So we can say that pressure is equals to force upon area. Pressure is directly proportional to force, whereas inversely proportional to area. When an object is submerged in a fluid at rest, the fluid exerts a force on its surface. कोई फ्लूइड रेस्ट पे पड़ा, अगर मैं किसी ऑब्जेक्ट को उसमें सबमर्ज करना चाहूँ, डुबाना चाहूँ, तो द fluid will obviously exert some force on its surface. This force is always normal to the object surface. Object surface के perpendicular act करेगा. This is so because if we were a component of force parallel to the surface, the object will also exert a force on the fluid parallel to it as a consequence of Newton's third law. This force will cause the fluid to flow parallel to the surface. Since the fluid is at rest, it cannot happen. Fluid parallelly move नहीं कर सकता, cause it is at rest. So therefore the force will act perpendicular direction and not in parallel direction. Hence the force exerted by the fluid at rest has to be perpendicular to the surface of contact with it. So whatever object is it acting, it should be perpendicular to that body, the point of contact. The normal force exerted by a fluid at a point may be measured. An idealized form of one such pressure measuring device is 10.B, that is this idealized device for measuring pressure. It consists of an evacuated chamber with a spring that is calibrated to measure the force acting on the piston. It's an evacuated chamber wherein there is a vacuum maintained, there is no air. The spring is calibrated. Inside that there is a spring which is calibrated to measure the force on the piston. This device is placed at the point inside the fluid. इसी डिवाइस को फ्लूइड के अंदर डाल देते हैं किसी पॉइंट पे. The inward force exerted by the fluid on the piston is balanced by the outward spring force and thereby it is measured. जितना फोर्स फ्लूइड अंदर लगाएगा उतना ही स्प्रिंग जो है वो फोर्स बाहर लगाएगी, and therefore they will be equal in magnitude, thus the force will be measured. The F is the magnitude of a normal force. मान लेते हैं कि normal force का magnitude F है, एरिया पिस्टन की A है, तो एवरेज प्रेशर जो होगा F by A होगा. That is already discussed. In principle, the piston area can be made arbitrarily small. जितना छोटा हम एरिया बना सकते हैं उतना छोटा बनाएंगे so that the pressure is more. Pressure is a scalar quantity. It doesn't have a direction. It just has a magnitude. It has to be either upwards, it has to be either downwards, it has to be either by the fluid or on the fluid. We remind the reader that it is a component of the force that is normal to area under consideration, not the vector force that appears to be the numerator. It is a component. The numerator force is the component of that force, not the vectorly thing. Its dimensions are m l minus 1 t minus 2. I repeat, the dimensions of pressure are force upon area, thus mlt minus 2 upon l square, that will give ml minus 1 t minus 2. The SI unit of pressure is Newton per meter square. Since Newton is the unit of force, we all know, and meter square is the unit of area, as we all know. It has been named as Pascal in the honor of French scientist Blaise Pascal, who carried out pioneering studies on fluid pressure. A common unit for pressure is the atmosphere or ATM, Pascal or PA, that is the pressure exerted by atmosphere at sea level. 1 atmosphere is the pressure exerted by atmosphere at the sea level, that is 0.1 atmosphere is equals to 1.013 into 10 to the power 5 Pascal, that is approximately taken as 10 to the power 5 Pascal. The exact value is 1.013 into 10 to the power 5 Pascal. Another quantity that is indispensable in describing fluids is the density. Density is the mass per unit volume. So its dimensions will be ml minus 3. Its SI unit is kg per meter cube. Kg is the unit for mass. Meter cube is the unit for volume, as it's already known. It's a positive scalar quantity. Liquid is largely incompressible and its density is therefore nearly constant at all pressure. Since there is a little compressibility with liquids, the density remains same all through. Gases, on the other hand, exhibit large variation in densities as it is compressible. The density of water at 4 degrees Celsius, I repeat, the density of water at 4 degrees Celsius is 1 into 10 to the power 3 kg meter cube, that is to be taken as 10 to the power 3000 kg per meter cube. The relative density of a substance is the ratio of density of that substance to the density of water at 4 degrees Celsius. I repeat, relative density. Whenever the term comes relative, that means in relation to something. So the density of the relative density of a substance is the density of the substance upon the density of water at 4 degrees Celsius. It's a dimensionless positive scalar quantity. As we know, it's relative, so it won't be having any units, won't be having any dimensions. For example, the relative density of aluminium is 2.7. So there is no unit. Relative density doesn't have any unit. So it's 2.7. Its density, when I talk about density of aluminium, we will say 2.7 into 10 to the power 3 kg per meter cube. But when it is relative density, we'll just describe it as 2.7. Done. Next. Example 1, 10.1 we are discussing. The two thigh bones, femurs, each of cross-sectional area 10 centimeters square, support an upper part of human body of mass 40 kg. So the weight of the human is 40 kg and the area, the cross-sectional area of the two thigh bones is 10 centimeter square. Estimate the average pressure. So what is pressure? It's force upon area. Area of one femur, that is one thigh bone, is 10 centimeters square. Humans obviously have 2 legs, 2 thighs, so 2 thigh bones. So 2 into 10 to the power 4 minus 2 into 10 to the power minus 3 meter square. We'll convert it centimeter square to meter square. Then simply divide it with the force, that is 40 kg. And if it is 40 kg, then the force has to be 400 Newton. As simple as that. Just divide 400 upon 20 into 10 to the power minus 4 meter square. And that the answer comes to be 2 into 10 to the power 5 Newton per meter square. That will be the average pressure. Pascal's law. The French scientist Blaise Pascal observed that the pressure in a liquid at rest is same all the points if they are at same height. So we talk about the scientist Blaise Pascal in fluids very often. He is a French scientist. He observed that pressure in a fluid at rest. Now, whenever I talk of fluid at rest, I am talking about hydrostatics. Am I clear with this? Whenever I am talking about fluid at rest, I am talking about hydrostatics. So, Pascal said that whenever we talk of fluid statics, we talk of fluid at rest, the pressure is same at all heights. The pressure is same at all points at the same height. At the same height, if there are 2 points, the pressure of both the points will be the same. That's all. He says that he said that if there's a fluid at rest, it's not moving, it's static, then at the same height, if I take 2 points, their pressure will be equal. As simple as that. Figure 10.2 shows an element in the interior of a fluid at rest. This element A, B, C, D, F in the prismatic element. So the thing, whatever this experiment is suggesting, the conclusion is, if the fluid is at rest at the same height, all points will have the same pressure. That's all. Hence, the pressure exerted is same in all directions in a fluid at rest. In every direction, it will be same. It again reminds us that other types of stress, pressure is not a vector quantity. Like other types of stress, pressure is not a vector quantity. I want you to make a note with this. Make the first note of this chapter with this sentence, that all stresses are vector quantities except for pressure. Pressure is also kind of stress, but it's not strictly not a vector quantity. Then I'll be talking of no direction can be assigned to it. Obviously, pressure would be assigned no direction. You already saw that it's not vector. The force against any area within the boundary of the fluid at rest under pressure normal to that area, regardless of the orientation of the area. Whatever the area may be, it won't depend on direction. As simple as that. The horizontal forces exerted at its two ends must be balanced. Okay, so let's talk of this. Now consider a fluid element in the form of a horizontal bar. Just consider that there's an element inside the fluid at any point, that the shape of the element is a horizontal bar. It's a bar. So what it says is, let it be a horizontal bar of uniform cross section. The cross section has to be uniform. The bar is in equilibrium. That means there is no torque acting, there is no force acting. It is in translational as well as rotational equilibrium. It is not translating, it is not rotating. As simple as that. No force, no torque. The horizontal forces exerted at its two ends must be balanced, or the pressure at the two ends has to be equal. If it is at rest, the horizontal forces has to be balanced. That means there is no net force, no net torque, and the pressure has to be equal on its two ends at the same height. The pressure has to be equal. This proves that for a liquid in equilibrium, the pressure is same at all points in a horizontal plane. Whenever I talk of a liquid at rest, the pressure will be same at all points in a horizontal plane. Suppose the pressure were not equal in different parts of the fluid, then there would be a flow, as the fluid will have some net force acting on it. If the pressure, just a common sense, that if the pressures are not equal at both the two ends, there must be some external force, there must be some net force, not external force, there must be some net force. And if there is a net force, there must be a flow of the fluid. Yes, and hence in the absence of the flow, the pressure has to be same everywhere. Since the liquid is not flowing, we are just studying hydrostatics this time, and we know that the liquid is not flowing. Since the liquid is not flowing, the pressure has to be equal, the forces have to be balanced. That's all. Streamlined flow. So far we have studied about fluid at rest, that is, we have studied hydrostatics. The study of fluids in motion is known as fluid dynamics or hydrodynamics. When a water tap is turned on slowly, the water flow is smooth initially but loses its smoothness when the speed of the outflow is increased. In studying the motion of fluids, we focus our attention on what is happening to the various fluid particles at a particular point and in space at a particular time. The flow of the fluid is said to be steady if at a given point the velocity of each passing fluid particle remains constant with time. This does not mean that the velocity at different points in space is same. The velocity of a particular particle may change as it moves from one point to other. That is, at some other point the particle may have a different velocity, but for every other particle which passes through the second point behaves exactly like the previous one. Each of the particle follows a smooth path and the paths of the particle do not cross each other. Variation of pressure with depth. Consider a fluid at rest in a container is at height h above the point 2. The pressures of point 1 and 2 are P1 and P2 respectively. Consider a cylindrical element of fluid area having base A and height h. As the fluid is at rest, the resultant horizontal forces should be 0 and the resultant vertical forces should balance the weight of the element. The forces acting in the vertical direction are due to the fluid pressure at the top, P1A acting downward, at the bottom, P2A acting upwards. If mg is the weight of the fluid in the cylinder, we have P2 minus P1 into A is equals to mg. Now, if rho is the mass density of the fluid, we have the mass of the fluid to be m is equals to rho v is equals to rho ha, so that P2 minus P1 is equals to rho gh.